We'll find out. It's recording. How are we doing today? Are you doing good in your calculus lives? What about your deep personal lives? You want to talk about those? Okay. I think we're on track to have a test 1 week from today. And I think we have finished through 4.2. And I'll be glad to take questions. We talked about finding extreme values on a closed interval in 4.1, and the mean value theorem, and Royle's theorem in section 4.2. Need a refresher? Section 4.1. We state the obvious, that if you have a continuous function defined on a closed interval, then it's going to have a largest value and a smallest value, an absolute maximum and an absolute minimum. If by chance the function is not continuous on that interval, or not differentiable on that interval, then there's no guarantee. You still might, but there's no guarantee. So for instance, let's see, does that look like I need it to be? Do you like it better with the light on in front or off? Anybody? Why is it backwards? All better? Now I got to flip that around. What makes that flip around? That one. That's flipping right way. Okay, so what we've done so far. Pencil? I got a pen. I'm not going to make mistakes today, am I? So, chapter 4 so far. Okay, in section 4.1, we said that every continuous function on a closed interval attains both its absolute max and its absolute min. And we don't just go hunting willy-nilly for them. We know how to find them. What happened there? Was that just me, or did that really happen? That was just me? We know how to find them. How do we find them? How do we find the max and min of a function? Find where the derivative is 0, or where it fails to exist, and compare them to the value of the function at the endpoints. So our candidates for the absolute max and min are the values of the function at the critical numbers and or at the endpoints. So we just compare the values of the function at the critical numbers and at the endpoints. So, like I might need one. Here, let's review, and then I have no examples ready. What's going on with that? Come. Let's see, did we do this one in class? Find the absolute max and the absolute min of the function f of x is equal to x to the 2/3 times 5 minus x on the interval from -1 to 8. Did we do this one yet? Zoom in. So we've got to make sure that we've got a continuous function so that we know that we're going to find them. X to the 2/3 power means we've got a cube root of a number that's squared. And we can take cube roots of every number in the world, right? Maybe not in our head, but cube roots are defined for positive numbers, negative numbers, and even the cube root 0. So x to the 2/3 is well defined, so is 5 minus x, and then the product of two continuous functions is continuous. So we do have a continuous function, we do have a closed interval. What we need to do is take the derivative of this thing and find where the derivative is equal to 0, and I suspect there's also going to be a place where the derivative doesn't exist, because I know when I take the derivative of an x to the 2/3, I'm going to get a negative power. Right? A negative power gives me a denominator. You can multiply it out, then take the derivative, or take the derivative using the product rule. It doesn't matter to me. I'm going to use the product rule. But what we need to be able to do is simplify this enough to find out where it's equal to 0. So try taking the derivative. Then write your derivative with positive exponents only, and then see how many critical numbers you get. I think you're going to get 2 critical numbers. Let's see if you do. Let's see if there's a way to get rid of this bad boy down here at the bottom. No. Okay. Critical numbers should be at x is 0, x is 10/3. Anybody doing those? I don't know, maybe I made it up. Let me do the product rule. So here's the first times the derivative of the second plus the second times the derivative of the first. So let's write that with positive exponents. So the x to the 1/3 goes down on the bottom with the 3. So I have negative x to the 2/3 plus 2 times 5 minus x. Times 3x to the 1/3. Let's write the right-hand side as a single fraction. Stop doing that. And so we're going to multiply that first fraction by 3x to the 1/3 over 3x to the 1/3 to get the common denominator. That doesn't work. What do you get when you multiply x to the 2/3 with x to the 1/3? Plain old x. So I got negative 3x here. They're all going to have the same denominator, so I'm going to go ahead and share it. Now I'm going to distribute the 2 here, and I get plus 10 minus 2x. Yeah, I don't know where the 10/3 came from. That should be a 2, shouldn't it? So I'm going to have 10 minus 5x on the top, 3x to the 1/3 on the bottom. So I know f prime is 0 when the numerator of the derivative is 0. And I know that f prime does not exist when the denominator is 0. So that first factor, 10 minus 5x is 0, occurs when x is 2. So I was just kidding when I said 10/3. And the only time x to a power is 0 is when x is 0. Those two critical numbers are both within the given interval. So I keep them both. And now we look at the value of f at each of those points, the two critical numbers and the two endpoints. Yes?
I solved it by setting equal to 0 before turning it into a fraction, like up at the top, but
Right.
we're still adding them together. And going that route, I got 2, but I didn't hit a point where I thought that 0 would be one of the. So should I just not
At
do
some
that?
stage in the game, you probably multiplied by an x to the 1/3, or
Yeah.
as soon as you're multiplying by x to the 1/3, you've got to make a note that x is equal to 0.
Okay.
It is a critical number because you're clearing a fraction, and that's only legitimate when x is only to 0.
Got it.
Right? You can multiply any equation both sides by the same number as long as it's not 0. Okay, so there's our two critical numbers, our two endpoints. We're going to plug them back into the expression for f. And so let me do this in table form. I'm going to put the numbers into x to the 2/3 times 5 minus x. So 0. The first factor is going to be 0 when x is 0, so that's going to give me y is 0. 2 gives me 2 to the 2/3 times 3. So that's 3 times, that's 2 squared is 4. That's 3 times the cube root of 4. Now x is negative 1. Negative 1 to the 2/3 times 5 minus a negative 1 gives me 6. Negative 1 to the 2/3 is a negative 1 squared, which is 1. Cube root of 1 is 1. So negative 1 to the 2/3 is just 1. That value is then 6. And then 8. 8 to the 2/3 times 5 minus 8 is a negative 3. Cube root of 8 is 2. 2 squared is 4. 4 times negative 3 is negative 12. That's my only negative number in the list, so that's clearly the min. Now we have to decide how big 3 times the cube root of 4 is compared to 6. Well, the cube root of 8 is 2, so the cube root of 4 is smaller than 2. So that number is smaller than 2 times 3. Agree? This number should be smaller than 2 times 3, so it's smaller than that one. That means 6 is our absolute max. Okay? So the idea is easy, knowing that a continuous function has a max and a min. The plan is easy, find the critical numbers, compare the y values at the endpoints and the critical numbers. It's the stuff in between, the implementation of the plan, that might take some practice, especially when you're dealing with things that are just not polynomials. So you know how to manipulate trig functions and things with funky exponents. Okay? So here's one with a trig function. Let's do the same. Let's find the absolute max and min. And let's look at f of theta is equal to the square root of 3 times theta minus 2 cosine of theta. And let's keep our interest on the interval from 0 to 2 pi. So again, I believe there are going to be 2 critical numbers. Let's see if you can find them. 2 critical numbers within the interval. We'll have to go to the calculator to find the value of f at those points to compare the size, because they're all real close. Getting 2 critical numbers? Anybody else? Here's the derivative. Everybody, I'm sure, got this. Derivative here is square root of 3. Derivative of cosine is minus the sine, so you get plus 2 sine theta. So now we're going to set that equal to 0. Get the sine of theta by itself by subtracting the square root of 3 and then dividing by 2. It's a negative number. Sine is negative in quadrants 3 and 4. Our reference angle for which we take the sine to get square root of 3 over 2 is pi over 3, so the version in quadrant 3 is pi plus pi over 3, which is 4 pi over 3. And then in quadrant 4, it's 2 pi minus pi over 3, so 6/3 minus pi thirds gives me 5 pi over 3. And those are both within 0 to 2 pi. Now we've got to evaluate f at each of those points. So I'm going to plug the value of theta in here, and then we put them in to the original equation. So we're going to go with 4 pi over 3. So square root of 3 times 4 pi over 3 is 4 square root of 3 pi over 3. Cosine of any pi over 3 is a half, but in quadrant 3 it's a negative 1/2. So negative 1/2 times the 2 will give me 1, and I'll make that plus 1. 5 pi over 3 times 3 will give us 5 square root of 3 pi over 3. In quadrant 4, the cosine is a positive number, so I'm going to have a positive 1/2 times this negative 2, which gives me a minus 1. Square root of 3 times 0 is 0. Cosine of 0 is 1, so here the value is negative 2. At 2 pi, I'll have 2 pi times the square root of 3, I'll write as 2 square root of 3 pi. Cosine of 2 pi is 1, and so I'll have a minus 2. And here are the numbers that we need to get off the calculator, and let's see if I did those. At 4 pi over 3, I think this is roughly equal to 8.3. At 5 pi over 3, this is roughly equal to 8.1. And then at 2 pi, this is 8.9. So they're all real close in value, but the 8.9 is the largest, and we only have one negative number, so that's clearly the min. So 8.9 is our max, and negative 2 is the min. So when both of our examples are max and min occur at the endpoints, but that's not always going to be true. And I'll have to give you better numbers on a test. You can't find these values on the test. But maybe I'll ask you to find the critical numbers, just to see if you can get the steps to do it. Okay, can anybody state the mean value theorem? Or roughly state the mean value theorem? Yes, sir.
If you have a continuous function from point A to point B, the average slope over the function, or just the total change in y divided by the total change in x, you will have some point in that function in which the derivative, or the slope of that point, is the same as the total.
That was so perfect. That was so perfect.
Does it have to be continuous and differentiable?
It has to be continuous and differential. We can't have things like we did in the first example where we had a vertical tangent line. It has to be in the world of math, when something has a derivative everywhere, that it's smooth. It has to be a function that doesn't have any creaky places in it. So if you have a continuous and differentiable function on some interval, somewhere the slope of the tangent line is equal to the average value of the function, f of b minus f of a divided by b minus a. So that's what we did in section 4.2. Says we have f is continuous on some interval from a to b and differentiable on the open version. Then there is some number c in the interval from a to b at which the slope of the tangent line is equal to the slope of the line through the two endpoints. Or the instantaneous rate of change is equal to the average rate of change. What's the difference between the mean value theorem and what we call Rolle's theorem? Go ahead.
Rolle's theorem is the mean value theorem, except the total change in y is 0.
That's right. It has 0 on the right-hand side over here. So the two y values are the same. So we're not even going to call it something different. We'll just keep it at the mean value theorem. Okay, so our job is to find that number c that makes the average slope equal to the slope of the tangent line. Okay, so my example here. Find the number c for which mean value theorem is satisfied if f of x is 1 over square root of 2x plus 1 on the interval from 0 to 4. But before you do that, this is a function that's a rational expression. So it's not continuous everywhere. Let's make sure it's continuous on our interval. Where is the discontinuity? At negative 1/2. Negative 1/2 gives us dividing by 0. So that's the only place that that's not continuous. It's a square root function, so it's also not going to be continuous at its endpoints, which again is at negative 1/2. Other than that, we're going to just have to believe that it has a derivative everywhere in the interval, right? Because the square root function looks like this, so 1 over the square root function should be the reciprocal. Should be some sort of hyperbola from negative 1/2 to infinity. So, I believe it's continuous and differentiable on 0 to 4. Maybe take the derivative by writing it as a quantity to the negative 1/2 power, and then just use the power rule. See if you can find that number c at which f prime at c is equal to f of b minus f of a divided by b minus a. It's a goofy number. It's not going to be a nice integer value. So I'm going to test your algebraic skills. So I suggest starting here to take the derivative. Something like that. So the half and the 2 cancel each other, and we can write that over. So I was right in saying that the derivative exists everywhere in the interval. The only place the derivative fails to exist is the same place where the function fails to exist, at negative 1/2 and beyond. So you're going to use that as the left-hand side up here. That's going to go in over here. You can replace the x with the c. And then we need f of b minus f of a over b minus a. So here's f of x. F of b will be f of 4. F of a is f of 0. And then you divide by 4 minus 0. Yes? Why? It should be negative, shouldn't it? Bring that 1/2 down. It should be negative. Good eye? Good eye on that one? This is a negative 1/2, so let's put the negative 1 there. So we have f prime at c should be equal to f of 4 minus f of 0 over 4 minus 0. So I've got minus 1 over, I'm going to use a C here. Let's find f of 4. On the bottom I'll have 2 times 4 plus 1. That's 9. Square root of 9 is 3. So I get 1/3 as my f of 4. F of 0 has a 0 right here. 2 times 0 plus 1 is 1. Square root of 1 is 1. 1 over 1 is 1. 4 minus 0 is 4. So the right-hand side is a negative 2/3 divided by 4. So that's negative 2/3 times 1/4 is a negative, just can't do math in my head. Negative 2/3 divided by 4 is negative 2/3 times 1/4. How about a negative 1/6? So you can cancel the minus signs on each side. Now we need to solve that for C. The C's in the denominator, so we need to get it out of there. What do you want to do? Help me, what's my next step? Cross multiply. So I've canceled the minus signs. So I'm going to have a 6 right here, and a 2c plus 1 to the 3/2 on the other side. So we're going to cross multiply and cancel the 1s. That times that times that. And so we have 6 is equal to 2c plus 1 to the 3/2. And here's where the goofy numbers come into play. I need to dig the c out of there, so let's get rid of the power. How do I get rid of a 3/2 power? Yep, raise both sides to the 2/3 power. And so we're going to have, I got to move over here, I'm running out of paper. So I'll have 6 to the 2/3 is 2c plus 1. We're going to subtract the 1, then divide by the 2. And so finally we get 6 to the 2/3 minus 1 divided by 2 is equal to c. We need to know if that's in our interval. We're told that it is. So I whip out a calculator, and I find that that value of c is about 1.15. And that is between 0 and 4. So the mean value theorem was not lying to me. There is at least one number in there at which the slope of the tangent line is equal to the slope of the line between the two endpoints. And so let's try one with a trig function. So the next one I'd like you to do is find the value of c for which the mean value theorem is satisfied. Let's go with f of x is equal to the sine of 2x plus the cosine of 2x on the interval from 0 to pi. Find the value of c in that interval at which the slope of the tangent line is equal to the slope of the secant line. Did you find it already? Anybody? And this one's actually Rolle's theorem because the slope of the line through 0 and pi is going to be 0. Or am I wrong? Sine of 0 is 0, cosine of 0 is 1. Sine of 2 pi is 0, cosine of 2 pi is 1. I'm sorry?
It's just pi over 2 pi.
Yeah, but when you put the 2 in, you put the pi in for x, it becomes a 2 pi. That 2 is going to give me f of b minus f of a is going to be 0. F of pi minus f of 0 is 0. Right? We need f prime at c to be equal to f of pi minus f of 0 divided by pi minus 0. We agree that this is a continuous function because sines and cosines are continuous, and so their sum is continuous, and they have derivatives that are sines and cosines, so the derivative is also continuous. So the derivative of sine of 2x is cosine of 2x times 2. The derivative of cosine of 2x is minus the sine of 2x times 2. So at C, I'm going to have 2 cosine of 2c minus 2 sine of 2c. Again, f of pi is 0 because sine of 2 pi is 0. Cosine of 2 pi is 1. Sine of 0 is 0. Cosine of 0 is 1. So this right-hand side is 0. Okay, so I'm going to move one of them to the other side and cancel the 2's out front. So I have where the cosine of 2c is equal to the sine of 2c. So we know the cosine and the sine are the same at pi fourths. So the 2c has to be pi fourths. They're also the same in quadrant 3. So pi fourths plus pi puts me outside the interval, but let's make sure that it's satisfied by 2c. So let's see. 2c is pi fourths, or 2c is 5 pi over 4. Now solve for c by dividing by 2, and I get pi over 8 and 5 pi over 8. Both of those are smaller than pi, so I actually get 2 values of c this time, at which the slope of the tangent line is equal to the slope of the secant line. And since the right-hand side was 0, those would be technically critical points for this function. Okay? Again, last time I did a bunch of polynomial examples, but I do expect you to venture out and mess with trig functions and funky exponents. Good? Well, what I'd like to do is the test that's 1 week from today to take it through here. Because the stuff that I'm going to cover next best fits together with the rest of Chapter 4, and I'd rather have that all in one test together. So your test 1 week from today will cover, where did our first one end? We had some derivatives on our first one, didn't we? We went all the way through 3.2. So exam 2 is going to be Tuesday, October 20th. Yep. It'll start with section 3.3. Chapter 3 went all the way through 3.8. And then the two sections in Chapter 4. So in section 3.3, we took derivatives of trig functions, logarithms, exponential functions. In 3.4, we did that business with a particle moving on the number line, finding its velocity, acceleration, distance traveled, and stuff like that. 3.5 was the chain rule, so more derivatives of compound functions. 3.6 was implicit differentiation, and with, I think 3.6 was implicit differentiation. Yes, and in there we got the derivative rules for our inverse trig functions, for logarithms of other bases, for exponential functions of other bases. And then we had that technique of logarithmic differentiation to take derivatives of things that look like a function of x raised to a function of x. So 3.6 had a lot in it. 3.7 was related rates. Right, so I'll probably just pick one problem out of there, and you'll have to let me know what's your favorite related rates problem. 3.8 was the linear approximation and the differential. So the linear approximation was just the equation of a tangent line, and we used it to approximate a particular y value. The differential was just the f prime part times delta x, and we used it to approximate the change in the function. Then in section 4.1 was the absolute max and min values of a function on a closed interval, and in section 4.2, this mean value theorem stuff. Okay, so the biggies are the 3.6. I guess 3.6 is really the biggie. The 3.5, whichever was the chain rule. And I'll put a review sheet on Blackboard as soon as I get back to my office and remember to do that. Yes?
I think we're on homework 8 now. Is that only for 4.1?
I don't know.
The only reason why I ask is because I figured you were going to send homework for the next week.
And I haven't put it on there yet?
Well, because we had a 10, but maybe you do. I was just going to ask if you could put up any problems from
I will.
something you did.
I will. I will. I thought I had, but then I don't know, I just don't. I gotta get on the ball here. What they did to me is usually I just copy my web work from a previous semester, boom, they're all ready. But somebody got ambitious over the summer and redid our web work programming thing because it was really old and a lot of problems had problems. So they redid it. And the new programming made all of the other problems not functional. So I can't copy my old homework and boom, they're there. I always have to start from scratch and go hunting for the problems that I want. And that puts me behind because that's the way I roll. So next semester will be great. I'll have them all ready. Okay, what I'd like to do next in section 4.3 is talk about the geometric interpretation of the derivative in terms of telling us what that describes function-wise. So I'm going to put up a graph here, and you draw it. We're using derivatives to sketch the graph of a function. We're going to have something called the first derivative test. We'll have something called a second derivative test. Both of those tests will tell us where a graph has a relative max or a relative min. So in this picture here, draw a graph that has kind of two little humps like that, down low, and a sharp corner. Because remember, in a sharp corner, we also have a critical number. So draw us that graph, and then we're going to draw some tangent lines to that graph. And we know that the slope of the tangent line is given by the derivative at that particular point. So I think I got a red marker here that I can draw some tangent lines. So over here, maybe at this point, I got to put some paper underneath this. At that point, my tangent line will look something like that. Does that line that I've drawn there have positive slope, negative slope? What kind of slope we got there? That's a positive slope, right? And it'll continue to have positive slope until I hit this hump. And at that hump, the derivative is going to be 0. So over there, the derivative is going to be positive. Once I pass that hump, my tangent lines lean downward. So the derivative is going to be negative until I hit the bottom of that hump, where the derivative is 0. Then it climbs again. Where the graph is climbing, my derivatives are going to lean upward, positive slope, then 0 slope. Where the graph is dropping, all my tangent lines will have negative slope, and then f prime is 0. Where the graph is rising, the tangent lines have positive slope, and then at the corner point, remember that you're not going to have a derivative. And this part is linear, all the derivative there is going to be negative. So as you read from left to right, a little bit bigger for me, we say the function's increasing when it leans like this. If you are running that as your running trail, you run uphill, so it's increasing. F is increasing on the intervals in which the sign of the derivative is going to be positive. F is decreasing or dropping on the sign, on the intervals in which the sign is negative. That's very much like what we did in the section on the motion, where the derivative was positive, the particle was advancing. Where the derivative was negative, it was retreating. Here, where the derivative is positive, the graph is climbing, and where it is derivative is negative, the graph is dropping. So what we're going to do is find where the derivative is 0, or where the derivative doesn't exist, and those are all going to be the critical numbers. We talked about absolute extreme values. A function has something called relative extreme values, which means in a small neighborhood around that point, a relative maximum exists if it's taller than all the points in that interval. The relative minimum will be where the graph is lower than all the points in that interval. If you look at our graph here, this point and this point and even this point will be relative maximums. They're taller than the ones around them. Down here I'll have a relative min, and here I'll have a relative min, because they're lower. So look at what happens to get a relative maximum. To get a relative maximum, you have to have a critical number, either where the derivative is 0 or where it doesn't exist. And the slope changes from a positive number to a negative number. To have a relative minimum, it has to do it the other way. You have a critical number, and the slope changes around that critical number from a negative to a positive. That's called the first derivative test for relative extrema. So in the first derivative test, let me use the number c to be a critical number. Let x is equal to c be a critical number for f of x, which means f prime of c is either 0 or f prime of c doesn't exist. So in words, if f prime is, let's see, I want it to be positive for x to the left of the critical number, and f prime is negative for x to the right of the critical number, then we know that f of c is a relative max. It's easier to say that in a picture form. In picture form, it says that if I have a critical number right here, and I want the sign of the derivative here, and I find that it's positive and then negative, positive here, then negative there, then that tells me the direction of f goes from rising to falling. So duh, f of c is a relative max. Now we're going to say it the other way. If the derivative is negative when x is on the left of c and positive when x is on the right of c, then I'll have a negative to a positive change. So let's just say it in diagram. If we have our critical number here and the sign of f prime goes from negative to positive, then the direction of f goes from dropping to rising, which tells us that f of c is a relative min. It's possible to have a critical number and the sign of the derivative doesn't change around the critical number, in which case then our critical number is not a max or a min. And we're going to do this for every critical number that a function has. And that will pretty much tell us what the graph is, if especially we have a polynomial where we know nothing weird happens. So in my next example, we're going to go through all the steps. We're going to find all the critical numbers. We're going to use those critical numbers on the number line, cut it up into intervals. Then we're going to check the sign of the derivative in intervals around the critical numbers, and that'll tell us the direction of the function. Once we know the direction the function's moving, we plot a few points, and we should be able to sketch a pretty good graph. We pretty much know what the graph of a third-degree polynomial looks like, right? It should go up, down, up. So we should find two critical numbers. Let's see if you can find them. F of x is x cubed minus 6x squared plus 9x plus 2. You find the critical numbers by taking the derivative and set the derivative equal to 0. Critical numbers, I think at x is 1 and x is 3. Anybody getting those? I did it in my head, so that's pretty dangerous. Got them? Then I can catch up with you. Okay. So first step in part A, find all critical numbers, means take the derivative. We get 3x squared minus 12x plus 9. I'm going to factor out a 3. Then I look for factors of 3, both with the same sign, that add to negative 4. And that tells me I needed an x minus 1 and an x minus 3 here. So my derivative is 0 when either factor is 0. So that gives me x is 1 and x is 3. So that's part A. Those two guys are the critical numbers. Now in part B, to give intervals where the function is increasing and intervals on which it's decreasing, I'll just do all that with a number line. The same way we found where the velocity was positive and negative. We put these two numbers on here, and we're going to plug them into the derivative. I'm going to put it into the factored form, and then I only have to hold the sign and not the number. That's a pesky little thing right there in the way. Pick a number in each interval, plug it into each factor, decide whether the factors are positive or negative, and then that should make your decision on the sign of the derivative. For example, in the first interval, a number smaller than 1 would be 0. When I put 0 in for x in each factor, both factors are negative. A negative times a negative is positive. So in this interval, the derivative is going to be positive. I'm going to use 2 as my test point in the next interval. 2 minus 1 is positive, but 2 minus 3 is negative. Positive times a negative makes my derivative negative in here. And then I'll use x is 4 as my test point for the last interval. 4 minus 1 and 4 minus 3 are both positive numbers. Positive times positive is positive. And so I'm going to use arrows to show the direction of the graph. It goes up where the derivative is positive, down where it's negative, and then back up. But let's get practice writing those as intervals. Where the arrow is pointing up will be the intervals on which f is increasing. So I'm going to write that first one as the interval from minus 1 to infinity, and then from 3 to infinity. So f is increasing on the interval from minus infinity to 1, and then again from 3 to infinity. It's decreasing between 1 and 3. So that's part B. Then we can just make the observation in part C to determine what type of extreme value occurs at 1 and what type occurs at 3. Where's the relative max? At 1. The relative min is at 3. Max, min. Okay, so in part C, we say we have a relative max at x is equal to 1 and a relative min at x is equal to 3. In part D, we're going to sketch the graph, so let's go ahead and plot those two values into the original function. F of 1 is 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2. So it's 1 minus 6 is a negative 5, plus 9 is a positive 4, plus 2 is 6. I don't know that I can do f of 3 in my head. Let's do it by brute force. F of 3 is 3 cubed. That's 27. 3 squared times 6 will give me a minus 54 here. 3 times 9 is 27 plus 2. 27 plus 27 is 54, so those add each other out. F of 3 is 2. And so let's put the graph right down here for part D. Doesn't have to be perfect. Of course, mine will be. We've got the ordered pair 1, 6 that I'm going to put here. And then we've got the ordered pair 3, 2 that I'll put here. Now with my pencil, I'm going to lightly draw in what the tangent line is telling me. The tangent line is telling me I have zero slope here and zero slope there. Then I need to make it rise, fall between 1 and 3, and rise up again. Those are my tangent lines. I've got a polynomial, so I know I can draw just a nice smooth curve through there. And it'll look something like this. We knew it looked like that before we started, because it was just a third-degree polynomial. Okay? So I've got you another one. I'm going to do the other one on a sheet of paper. X squared minus 10x all to the third power. If I was goofy enough to multiply that out to the third power, I would get a polynomial. What would the degree of that polynomial be? Should be a 6th-degree polynomial. So a 6th-degree polynomial will probably be something like that, right? But we'll find out. I want you to take the derivative. Just use the chain rule there. Take the derivative. Get your derivative as factored as you can get it. And tell me how many critical numbers you have and what they are. I'm going to move that to a blank sheet of paper. If I can find a blank sheet of paper. No, try to keep things factored. Try to factor your derivative as much as possible. It would be nice if one of these things gave me a light. But neither of them do. What do you think AF stands for? There's a button that says AF. Autofocus. And then the other one is AFL. And none of them's a light. I would like a light right here. Oh well. Can't have everything. I'm going to catch up with you. So we're keeping it factored, right? Which means I'm going to take the x squared minus 10x now in the next step and factor that as x times x minus 10. And I'm going to take the 2x minus 10 and factor it as 2 times x minus 5. I'm going to put the 2 with the 3 and make me a 6 out there. Both the x and the x minus 10 are squared, so I'm going to write them individually as squared terms. So 2 times 3 gives me 6. Then I have an x squared. Then I have an x minus 10 squared. And then I have an x minus 5. So there's our derivative. We're going to set our derivative equal to 0, and our critical numbers will come from setting each factor equal to 0. So f prime is 0 when x squared is 0, x minus 10 is 0, and x minus 5 is 0. The 6 is never 0. The only number you can square to get 0 is 0. The next one gives me x is 10, and the third factor gives me x is 5. So my critical numbers are x is 0, x is 10, x is 5. That's part A. In part B, we analyze the sign of the derivative around those. So let's draw us a number line, put our critical numbers in order, 0, 5, and 10. We're looking at the sign of f prime, and I'm going to put it in its factored form here, because the factored form is really helpful to me. I see, if I get it away from all these obstructions here on my screen, that one of my factors is to the first degree, the other factors are to the second degree. Those second degree factors, no matter what I plug in for x, are going to be positive numbers. So I can quickly check the sign of the derivative just by finding what happens to the sign of this last factor. The last factor is going to be negative when x is smaller than 5. Positive when x is bigger than 5. Agree? So I can whip the signs out real quick. Since my first two factors are positive, and I know x minus 5 is negative when x is smaller than 5, my sign chart should look something like that. Which means the direction of the function, which I'm going to draw under the line, is that it drops. It continues to drop even though the slope here was 0. So I've got a horizontal tangent line here, but negative slopes there. Then I've got a horizontal tangent line here and positive slope, another horizontal tangent line, but more positive slope. And so I've got the function increases where the arrows are pointing up. And that's between 5 and 10 and beyond 10. Between 5 and 10 and then again from 10 to infinity. So it wouldn't be right to say from 5 to infinity because it's not increasing when x is 10. So I have to write it as two intervals. Be careful if you're on web work. If you just say from 5 to infinity, web work will say, right? There's no slope, there's no sign at x is 10. Then it decreases to the left of 0, and then again between 0 and 5. So in part C, make the observation and tell me where you have a relative max. Do we have any? Do we have a relative max anywhere? Nope, there is none. It doesn't change from rising to falling. Never in my picture does it change from rising to falling. So there is no relative max. We do have a relative min. Where? At x is 5. And so we're going to plot those points to sketch the graph. The points I want to plot are 0, 10, and 5. I'll do 0 and 10. We're going back to F. Come back here, F. Where are you? Where the F is F? There's F. F of 0 is 0, and F of 10 is 0. Now it's your turn. Tell me what F of 5 is. Five squared minus 10 times 5 is a negative 25 minus 50 is 25, and then I got 25 cubed. I don't care what 25 cubed is, I'll just leave it like that. It's a negative number though, isn't it?
Big negative.
Negative number, big negative number. So don't draw your graph to scale. Let's draw the picture. And let's see, everything's happening over here. I don't need a negative axis. Let's go here. F of 0 is 0. F of 10 is 0. And f of 5 is a big negative number. Now, I've got to make the graph drop. It's got to get a horizontal tangent line here. Then it's going to continue to drop, and another horizontal tangent line. Then it's going to rise, horizontal tangent line, and rise some more. So it's not going to be your basic parabola. It's got little places where the graph kind of acts like it wants to turn around, and then says, nope, it's going to come down. And then it's going to turn around, act like it wants to turn around, and then change its mind and go back up. So it should look something like this. Come on down, flatten out, and then say, whoop, get back down here. And then come down, come back up. It's doing all this in a smooth way. So those are just two little buckles there. They're not sharp, they're nice and smooth. Okay? Now, the graph turns around at this critical number, and what you'll find is that it changes something called the concavity in there. If you take a wire and bend it so that it would hold water, then that part of the wire is said to be concave up. If you take a wire and bend it so that it would spill water, like that part of the graph would be concave down. Where the graph changes from concave up to concave down is a point called the inflection point. Let me put a picture up here. The concavity of a function will be determined by the sign of the second derivative. And let me show you why. The first piece I've shown you is an exaggerated portion of a graph that's concave down. And in the second piece, I've got a graph that's concave up. And then in the third and the fourth pieces, I've got some that change from concave up to down and down to up. So on this interval, if the graph is shaped like this, f is concave down. And here, f is concave up. Now let's look at the derivatives on a portion of the graph that's concave down. The derivatives are the tangent line. So if I draw you some tangent lines here, they start out with some positive numbers, then the derivative becomes 0 and becomes negative. So f prime changes from positive to negative on an interval in which the graph is concave down. On the graph that it's concave up, the derivative is going to start out as some sort of negative number and then become positive. So where it's concave up, you'll see that f prime changes from negative to positive. So the graph is concave up, where f prime grows in size from a negative number to a positive number. So f prime is increasing. We used f prime to tell me where f was increasing. I'm going to use f double prime to tell me where f prime is increasing. F prime is increasing where the sign of f double prime is positive. And then, to emphasize this follows the same pattern, f is concave down where f prime changes from a positive number to a negative number. So f prime is decreasing, which means its derivative, f double prime, is negative. We're going to analyze the sign of f prime and f double prime the same way we analyze the sign of f prime. We're going to take a second derivative. We're going to find the values of x at which the second derivative is 0. Those numbers are going to be called inflection points. On one side of the inflection point, we'll get the sign of the second derivative. We'll get the sign of the second derivative on the other side, and that'll help us to decide where the graph is concave up or down. The graph is concave up, where f double prime is negative. I'm sorry, I just said that backwards. Concave down, where f double prime is negative. Concave up, where f double prime is positive. Okay? So in the next two pictures, I've got an inflection point right here. If that were a wire, the point that feels the stress where it changes from concavity is the inflection point. And what those pictures are supposed to show you is the concavity doesn't tell you where the graph is increasing or decreasing, only where it's concave up or down. The first picture shows a decreasing part of the graph, and the graph is decreasing but concave up here, and decreasing but concave down there. It doesn't have to be such a harsh change as my first two pictures. The second shows a portion of a graph that's increasing, and it changes from concave up to concave down by around that point there. So we've got two separate tasks. We've got to use the first derivative to tell us where f is increasing or decreasing, and then we're going to use the second derivative to tell us where the graph of f is concave up or concave down. Okay, so in our first example, we had that third degree polynomial that looked up, down, up. It only changed concavity once. We should have one inflection point. So let's go back to our first example. We've already got the critical numbers. We've already got where it's increasing and decreasing. We've already got the relative max and min. Let's start with the first derivative and find where it's concave up or down. So the function from our first example was, where'd it go? F of x is equal to x cubed minus 6x squared plus 9x plus 2, and our first derivative was 3x squared minus 12x plus 9. So we did all the stuff with that. Let's go ahead and jump to finding the inflection points. The second derivative is just 6x minus 12. You set the second derivative equal to 0 and solve for x. Add 12, divide by 6. We get that x is equal to 2 is the inflection point. And what we're going to do now is make a number line with our inflection point on it, but this time we're going to check the sign of the second derivative. So here's my second derivative right here. Pick a number smaller than 2. plug it in for x. If I put a 0 in for x, I get a negative second derivative. If I pick a number bigger than 2 and plug it in for x, like a 3, I get a positive number there, which tells me the concavity. That it's concave upward, concave downward, where the derivative is negative, concave upward, where it's positive. So let's go back and look at that graph. Here's the graph we had. Our inflection point is going to be right in between these two at x is equal to 2. There's my point of inflection. Notice that the graph over here is concave down, and then it becomes concave up. Okay? So it didn't tell us anything new and exciting. I don't want to do the second derivative for our other example because I have like 3 factors. It would take me forever to multiply that out. We don't have forever. In fact, time's up. Was that enough for you today? I can stay another hour if you want me to. Don't twist an ankle running out of here. You guys got to warn me because see, my clock says now it's like 20 to 1. It's getting closer though. It's no longer nighttime.
How were you able to give us an email while you were teaching?
I'm sorry?
How were you able to give us an email while you were teaching?
Did I? Oh, what did you tell you?
We're going to have to go back after Thanksgiving.
We got 1 class after Thanksgiving, but I'll miss you doing it. We'll do this.
Actually, I'm thinking about it. The only classes that I'll be missing that would have been in person is Dan. Well, I don't think we're doing that.
Well, yeah, it doesn't make sense to come back after Thanksgiving.
I was looking on the classes for next semester.
Hello?
Said yours is online.
I don't think it is. I gotta look. I haven't looked, so I don't know.
I didn't think it was going to
If
be.
it's an honor section, honor sections are not online.
Yeah, so that's what I asked you.
Yeah, I haven't looked. I have to find out. Oh, very good. Very good. I like that. Thank you.
I thought of it and I was like, I like this a lot.